Our next speaker is Professor Shinkyu Park from our own KAUST. He is from the Distributed System and Autonomy group here, and he will be talking to us about robotics and automation in coral monitoring and restoration. Please, Professor Park.
All right, thank you so much for a nice introduction. So again, my name is Shinkyu Park, and I'm assistant professor here at KAUST. So I work with control systems and robotics as pretty much the applications. So what I want to do today is to briefly introduce some of the research we are doing at KAUST, especially in the risk lab. So unfortunately, we are actually running out of the time. So I'm sure everyone is hungry here, so am I. So I'm going to make my presentation as brief as possible, but I'll open the floor for the discussion and possible collaborations during the lunchtime. So what we do at the risk lab at the KAUST is we actually build the robots and do a lot of experiment with the collaboration with our colleagues, especially when it comes to underwater robots. We actually work closely with our colleagues at the Rescue Research Center. Next speaker, Professor Raquel, will tell a little bit more about how the biology side would think about working with a robotics side. So, but from my presentation, I will talk more about the robotics research. So our primary goal is to build a robot that can somehow automate some of the typical process that we are facing in the coral monitoring and the restoration process. So I'm going to talk about underwater robot that can monitor the underwater coral reef environment. Also, I will briefly talk about the manipulations that can be used for automating some of the coral restoration typical process. So before I move on to the technical part, I want to briefly mention who we are. So my name is Shinkyu Park, and I'm one of the faculty in the risk lab. I also have my nice colleague, Professor Eric Perron, who is the main organizer of this conference. So Eric really likes the flying machine. I like things that goes under the water and also things running on the ground. So I tend to work with the ground robots, but I try to extend my research interest when I joined KAUST, going underwater, but I really hate the swimming, by the way. So the other thing I wanted to highlight today is actually we have a really nice group of researchers, including students, postdoc, and research scientists, and also research engineer. So I want to thank many of them to helping us to organize this beautiful conference, and I'm sure they are running around this campus to make this conference to work out. So I really want to thank them before I begin my presentation. In terms of research, we try to look at the different themes, and our primary purpose is to actually train our students to become competent researchers. So we try to look at the different aspects of the robotics and also the control system research, and there are some of the ongoing work working with the drones, underwater robots, and also the robotic arm manipulation research. Okay. So before I begin my technical part, I want to briefly talk about feedback control design. So I'm sure there are some people here who has a theory in the theoretical background in the control theory, but the beauty of the control theory is you really have a system. Say I have a robot, I design a feedback loop, I close the loop. What happens is I can actually make a robot stable, and I can actually make the influence of noise that coming into our system reduced. So what do you mean by stabilizing the system? What do you mean by reduce the influence of the noise to our system? So I briefly show you some of the video I have been accumulated over time. So this is one of the projects I did when I was a postdoc, right before I came to KAUST as a faculty. So we are actually building autonomous surface vessel that can navigate in cities canal environment. There is like a small coral that is pushing our vehicle. So here, primarily, we want to design the feedback loop in a way that if something is pushing our vessel, we want to make sure the vessel is trying to recover its intended location or intended trajectory. So here, what we are trying to leverage is we leverage some of the theory from the robotic control in order to see how fast we can recover when the vehicle is pushed away. So this is kind of a younger version of myself, like 4 years ago. All right. And the other research I did in the past was what happens if we apply the feedback control principle to multi-robot navigation problem. Here, the way this simple system works is each robot sees how the other robots are trying to avoid a collision with themselves. And the simple mechanism we implemented is if my opponent is coming to the left-hand side, I have to avoid oncoming robot on the right-hand side. So this is a very, very simple implementation, but as we build a feedback loop between the robot, it actually guarantees a collision avoidance. And the last one I want to briefly show is a multi-robot task allocation problem, where we have a robot with an arm and they have a computer vision system. So if it sees something on the ground, it extends the arm, grab it, and put it into the pocket. And you might imagine this implementation would require higher level of like communications and coordination, like a sophisticated software in order for just multi-roles to coordinate. But the simplest idea you can implement in this system is actually, if I pick up something, I just let my colleagues know that this is an area I already picked up the object on the ground, so don't come here. So this is a very, very simple algorithm implemented. Of course, I don't want to claim that this is the best way to do the coordination between the multiple robots, but this is one way. We use a feedback control policy, feedback control principle to implement it, and in practice, it works well. It works up to a certain degree of performance. So what I want to do today is I'm going to present some of the research we are doing on the underwater robots, where main tool we are using is the feedback control theory and also the manipulation work. We use the feedback control theory in order to build a system and do some interesting experiment with it. So our goal in the underwater robotics projects, we want to actually build the underwater robots that can be used as a remote imaging tool. I think many of the concern that marine biologists they expressed during the presentation was diving is very, very difficult. So each time I talk to a student from the research center, all they claim is they like snorkeling, but they don't like diving for data collection and doing research. So what we really wanted to do is build an autonomous system that can actually assist the researcher to collect the data. And the other part is we want to bring the vehicle as close as possible to the underwater structure. So there is some of the safety issues that arises. And also toward the end, we want to actually make a large number of small vehicles and use a simple coordination system for them to monitor the large scale area. And here, when we talk about like a large number of vehicles, the coordination becomes very, very important. But on the other side, if you have sophisticated system, the point of failure becomes very, very critical. So we want to develop a system that is simple implemented, but achieve the high level of coordination in data collection. So there are some of the engineering challenges. I'm sure those are some of the things we have discussed in the previous slide, at the previous presentation. So I will skip some of the engineering challenge we already know. And the solution we come up with, let's try to build a autonomy on the single vehicles as much as we can and leverage the autonomy of the single vehicles and use a simple coordination algorithm. And the coordination algorithm has to comply with some of the engineering challenges in the underwater communication. Maybe if you try to send the image data, that might not be transferable because it's a huge data amount. And also asynchronous communication might be another challenge we have in the underwater robots. Say I want to transmit something to my neighbors, but sometimes the transmission does not happen, or the transmission would interfere with the other robots' communication. So we are trying to come up with a simple algorithm for the coordination, but mostly leverage some of the autonomy, the capability of the individual robots. So there is actually a snorkeling trip scheduled for tomorrow morning. So most likely this is what you are going to see when you go to the snorkeling trip. So probably if this is the first time doing snorkeling trip in the Saudi Arabia, you will see something amazing. So one of the tips I can tell you is if you want to distinguish between the live coral and the dying coral, is just to look at the surrounding and see if you see a lot of fish. The healthy coral around it, you see a lot of fish still, but you see, coral that is a little bit gray or whitish, you will see less fish that surrounding it. But still, the coral reef in front of the KAUST campus is exciting, but there is some of the some of the challenges we have to come up with. So what we are trying to see is whether we can build smaller vehicles possible and send them to collect the data, try to the data to inform some of the policies we have to refine or come up with a new policies for saving our coral. Okay, so we actually started with buying some of the platform from this company called the Blue Robotics and tried to do some modifications. The size of the vehicle we have is slightly wider than the regular Blue Robotics platform. We had to put some of the extra electronics and sensors inside. And other than that, I think we are pretty much using a regular electronics that the company sells. And only the difference is we put a DVL sensor and the stereo camera in order to the underwater imagery while the robot is moving around the underwater environment. And we spent a lot of the time to think about how we can actually nicely build a feedback loop around individual robots. So here, we actually have two feedback loops. And one is around the robot and the sensor fusion and the controller. And the other part is actually, between the robots. So if they are sharing information through the communication channel, that will just form another occasional feedback loop between the multiple robots. So here are some of the experiments one of my students did in one of the diving pool on KAUST campus. Here, what the robot is trying to do is it uses the DVL sensor in order to position itself at a fixed location. So I'm just showing this video, but we spent almost a year to reach this point. Now I'm understanding why the underwater robotics research is very, very difficult. And there are so many things can go wrong underwater. So we have lessons learned, and we are actually moving forward with a nice test experience. And when it comes to using the stereo camera, one of the things that we are actually leveraging is that there are some of the nice products out there that provides not only the physical camera itself, but also the software it comes with. So to be honest, this is not something we have actually developed in the lab, but we're actually leveraging some of the existing technology for the imaging systems. So here we are using a stereo camera, and along with the software it comes with, try to see if we can map the structure of the diving pool. So here we are only relying on the computer vision, and surprisingly, it works pretty well, given that there is effect of the light, and there is actually no a visible feature on the surface of the swimming pool. So most of the computer vision algorithm that works in the robotics research, they have to see some of the features in the environment in order to identify where the robot is and try to build a map around it. Okay. Okay, so we are still, moving forward with a developing system and making autonomy at the level we want. But in parallel, what we want to do as a research problem is we want to think about how we can use a multiple of them to monitor the large area coral reef environment. So one of the research questions we posed in our research project is, what if we have a large area, we want to operate the multiple robots, and individually they want to collect the image of the coral, and we are going to bring the data back to the KAUST campus, and some of our researchers will analyze the data, try to build a 3D model of the environment, and also identify the coral species. And once you have a result, we'll push it back to our system and see if we can iterate this process to improve the system performance. So when it comes to operating the multiple vessels, communication is one of the critical components. And assuming that the communication on the water is very, very difficult, in a sense that sometimes if you try to send the data from one robot to the other, the packet might be lost, or synchronization between the robots might be very, very challenging. Maybe the interference would be the source of the challenge here. So we thought about, given the limitations on the underwater communications, how we can do the coordination between the robots. So our approach is we think about how humans are actually behaving in our society. So say we have a room of people here. I have to ask, as one of the organizer of this conference, lunch is ready out there. I'm not going to tell individual people to line up and go through the door and then get your lunch. Probably what I'm going to say is there are 3 doors in the room. You can take any of the rooms, and lunch is out there. And then you will become an autonomous agent for you to determine which door to pass and which line to line up in the lunch line, right? So same thing for our underwater robots. As long as we have a certain level of autonomy for the individuals, maybe we don't really have to tell individual robots where to go. We just let them know that there are coral species you can possibly identify and collect more data around it. Of course, there is a lot of underlying theory we have to think about, but one of the principles we are using is not only the feedback control principle, but we are also looking for a way to what we call the game theory. We leverage some of the things from the game theory in order to understand what is a mechanism, what is the incentive mechanism we have to develop to leverage the individual level autonomy in enabling the coordinations in our underwater robotics project. So here, one of the key challenges, we have to come up with a model for how the robots are making decisions to go where to collect the data, and also to coordinate among them through the incentivizing mechanism. I will not go into any of the details, but there are some of the criteria we set and we are trying to meet and use it for the designing models we have. And mathematically, this is really the two-line expression you can come up with. But underneath, there are a lot of the things we have to understand. Some of the variables represent the reward we have to give to our machines. But in order to compute this reward, we have to really think about what sensor data they're getting and how they are communicating with each other. And there is an underlying some of the optimization problem we have to solve. But I will not go any of the details, but I want to show you some computer simulations that how this approach would work if this were applied to the underwater robot project. So in terms of the implementations, the big picture is another feedback loop, but inside one side we have the modules that is related to the autonomy of the individual robots. On the other side, there is communications and there is coordinations among them. So I will not go in any of the details, but the bottom line here is we can nicely fit individual autonomy component along with the coordinations. So you might want to ask, what happens if the communication between the robots is completely not possible? Would it still work well? So in that scenario, the approach would mainly rely on the autonomy of the individual robots. Of course, the coordination will not happen. So maybe if a robot goes to the A location to collect the data, another robot will go to the same location, but the system will not fail. Okay, so in terms of the data efficiency, if we allow more the communication between the robots, then the level of coordination go high and the data efficiency will go high as well. But even if we don't have higher frequency of the communication between the robot, we still can have the system running without much failure. Okay, so this is a computer simulation. So I'm not going to claim that this is something we have tried with the real robots, but hoping this is pretty much what we're going to see once we do the experiment out there. And here the scenario is we have 4 patches. So maybe the patch can be understood as like one small area of the large scale coral reef. And we are going to deploy like 40 robots here. And here the communication does not really need to happen, but the way I did design the simulation is the communication between the robot within the same patch will happen more frequently. Across the patch, it will happen less frequently. So I will not go into the details. If you want to learn more about the simulation setting I did, I will happy to explain during the lunch break. And the other part is we have a data collection station. So the robot has sufficient amount of data collected, and it will, return back to one of the nearest data collection stations, and they will release the data, but also they can use this station to recharge their battery. And if something goes wrong, they can fix at the station. So as long as the robot can navigate itself and collect the data and can return back to the station, this algorithm, this approach will work well. Okay, so here is the computer simulations. The blue dots represent one of the underwater robots. And this red patch represents depending on its intensity. If it is darker, that means that there is more data we have to collect from there. So there is actually the underlying model we are running behind the simulation, but as long as the model best represents what is real phenomena that is happening underwater, this approach would work well. And the only thing they are sharing information is I've been to a location and I let other robots in the same patch that this is the place I went. So you don't want to go there. But none of them are actually telling other robots where to go, or none of the robots are telling other robots where to go. So you might want to ask, so this is actually the scenario where they start with less data to collect. And I will jump a little bit to the later portion. And at some point, maybe there is an event that would draw much of the attention of the robots. So we have to move the robots to some location to collect a lot of data. Maybe there is a bleaching event that is happening in one of the patches. So here, instead of telling robots to go some location, we just inform the robots that there is a bleaching event that's happening in one of the patches. You might want to go there because there's a lot of data we have to collect. So instead of really telling the robots, giving the step-by-step instructions, so this algorithm allows robots to think by themselves and make a decision where to go. So this, like a low level, like a simple coordinations, allows this large team of robots to coordinate in this data collection deployment scenario. And of course, because we are using very, very simple coordination algorithm, it scales well. So previously we had a demonstration with 40 robots. Now we have a demonstration with 90 robots. Only the issue when I run the simulation is because I have to run a lot of, just the blue dots in the simulation. Running the single simulation in the small computer will take some time. But if this were really implemented with underboard robots, then individually they can just make a decision based on the information this is available to individual robots. Okay, so there are some challenges we have when it comes to deploying the system for the real robots. There might be a case when there is a delay in sharing informations, or because this is a physical robot, they have to move one location to the other. So if I have to ask robots to go from one location to the other, oftentimes what happens is they spend more time in the traveling between the places rather than collecting data for useful purposes. So there are some of the still challenges we have to tackle, but we are still making progress along the way. Okay, so I want to briefly talk about the coral bleaching. So we are already aware of the series of the coral bleaching, and yesterday we had a very, very nice presentations of the negative impact of the coral bleaching to our local society. And this is actually one of the figure I use to educate my children. So my children is attending the KAUST school here at campus, and one of the activities they are doing is visiting the research center to understand why the coral is important. So I actually asked my son, I show you this picture, and I asked him which side is better. So I didn't tell anything more specific. I just tell my son which side is better. He was actually telling right-hand side is better because it look brighter. So when it comes to the coral bleaching, I think one of the important thing we really have to realize is the coral bleaching is not just a change of the color, it's really destroying the natural habitats of our the marine species. So when it comes to teaching my children why the coral bleaching is really, really serious is, fish are losing their house. I also ask, what happens if we lose our house? Are we going to survive? Of course, the children's answer is no. So does fish. If they lose their house, we are no longer going to see fish. So with that, some of the effort we are making in the KAUST is actually some of the work that my colleague at the Charlotte Hauser's lab, they're actually looking for a way to expedite the coral restoration process. So some of the research we've been thinking about the collaboration is what happens if we can use additive manufacturing to create one of the coral structure that looks like a real coral structure, and then use the microfragmentation technology to put the small fragment of the live coral on the structures and grow in the nursery. Of course, it can be scaled up, but still, I think one of the presentation in this session was thinking about scaling up the coral restoration process. Other than just printing out the structure and putting the micro fragment, there are a lot of the manpower that needs to be done. Like one of the things I heard about the labor-intensive operations in the coral restorations is really the cleaning up the water tank and also the cleaning up the excessive algae on the, this growing coral in the nursery. So we thought about what if we can adopt robotics technology, especially the manipulations, to automate some of the labor-intensive work in the coral restoration process. So some of the requirement for this robotic system to work well in this environment is robot needs to interact with a physical environment. And the other part is there are some of the computationally difficult tasks we have to implement on our engineer system. As a human, probably if you see this type of a figure, and we can actually think about what is the steps you have to do in order for this coral restoration process to set up. But from the robotics perspective, robots are not as smart as a human for now. So we have to really program step-by-step instructions into the robotic system. And so there are some of the computational challenges we have to overcome in order to adopt a robotic manipulation. So there has been a lot of work that has been done in terms of enabling the autonomy of the robotic manipulation. So there are some of the work that has done in the AI research community, thinking about using robotic hand to solve the Rubik's Cube and playing the piano, drawing, throwing the object, and different way to do the additive manufacturing. But one of the things my research group is focusing on is actually the robot assembly. So I have different pieces on the table, how I can teach the robots to pick up one of the pieces and then put them together to build the product we are intending to assemble. And the general pipeline for the robot assembly is we start thinking about using the sensor to identify the object we have to manipulate. And once you have identified the object, we think about how we can put the one object to the other in order to do the assembly. And once the planning is over, we actually have to do the execution. So there's sensing part, there is a control of the motor, and there is some of the path planning we also have to do to move around the robotic arm. And one of the things I want to talk about is actually the planning part and also the controlling arm. Of course, this robot assembly is way more complex than what we need for the coral restoration. But I think some of the lessons we learned, some of the systems we design can be applied to some of the labor, to replace some of the labor-intensive process in the coral restoration. So we are trying to see we can use a robotic arm in the coral restoration process. Okay, so in terms of the sensing, I want to briefly introduce the system what we have in our lab. So we installed a high definition camera. So if you see the figures on the left-hand side, this is actual sensing reading from the camera we have. So it has a really, really high resolution. But the only issue we have is in order to take a picture, it takes about 1 or 2 seconds to get a high resolution camera. So if you actually do the experiment, what would happen is if we have a static object on the table, the robot has not much issue with identifying its object itself and its location and extend the arm and do the pickup. It's a not very difficult task. But while the robot is sensing, identifying the object on the table and try to extend the arm if somebody is slightly pushing one of the objects on the table, then most likely the robot is not able to pick up anything. So one of the challenges we are trying to solve is camera system is great, but there are some challenges with the frequency of the sensing part. But what if we can use a different sensing modality in order to disclosing the loop frequency more often? So instead of, in addition to the high definition camera we are using, our system also have the tactile sensor. So we are trying to see if we can leverage both high definition camera system with a tactile sensor in order to better interact with the physical objects in our manipulation task. So there are some other work we've been working on how to think about. There is a number of steps we have to do, but what is the optimal way to set up the steps in order to go from individual pieces all the way to the final product? So there are some of the work my students are working on to address some of the computational challenge, but looks like I'm running out of time. So I will skip this part, except here. So the basic, the underlying principle here is if you think about doing some assembly, so I have to solve like a 3D puzzle. I have a piece, I have to put them together to put it in the right way. And if you try this puzzle over and over again, what you realize that you are actually getting the skill sets to solve the problem. Even if the pieces are slightly different, you're actually picking up the pace and you are actually learning something from your past experience. So we are actually using that principle along with some of the recent tools in the machine learning in order to understand what's the best model to teach robots to do assembly and how we can do computationally. So there are some of the work my students have been done in order to teach the robots to the simple assembly. And we are hoping we can do more complex things that includes, putting the micro fragment on the coral and then putting the, restored coral into the nursery, so on and so forth. So those are some of the, application we are looking for out of this robot assembly fundamental research. Okay, so I will stop my presentation here. And I personally want to thank the members of the Risk Lab organizing this conference and also contributing to some of the lab project. And the other part, I want to do special thanks for my colleagues at the Research Center to do the collaborations on many of the project and also their support. Thank you so much for your attention.